Welcome to a code report presentation. In this YouTube video, I'm going to be representing a talk that I gave 2 different times in the past couple of weeks, once on September 1st in Toronto and once on September 7th in New York. The title of that presentation was a look at array languages where I compared APL versus BQN versus J. So 2 quick notes. There are 2 different repositories on my GitHub. The first one is content, and you can find all of the slide decks and material for this talk there. On top of that, there's another repository called Array Language Comparisons where this example plus a bunch of other examples across not just these 3 languages, but also R, Julia, NumPy, Nial, Single Assignment C, Futhark, and Q. You can find comparisons of those languages on that repository, as well as what's being covered in this video. So if you're interested, check those out. Links will be in the description down below. And the final thing to note is that in the presentation that I gave the last 2 times, I just looked at the languages APL, BQN, and J. But in this presentation, I'm going to be sort of giving an extended version of that talk where I compare APL, BQN, and J, just like I did in the previous 2, but then also R, Julia, NumPy, and at the last minute, I also added Q. So with that out of the way, I'm going to do a brief introduction of myself in case this is the first video of mine that you are stumbling across. I've been in the industry for 10 years now, and I've been working at NVIDIA for the last 3. I just joined NVIDIA Research as a research scientist, and for that time, I have been a professional C++ developer for the entire duration. I've picked up other languages along the way, but my primary language of implementation has always been C++. While I was at Amazon, I joined a functional programming study group, at which time Haskell became my favorite programming language. And then over the last 2.5 years, I've been studying basically array languages, and APL was the first one that I looked into, and these have become my favorite programming languages by far. I have a YouTube channel that I started 5 years ago, a Twitter account that I started 4 years ago. I have a programming languages virtual meetup that goes through different programming related textbooks. And on top of all this, I also have 2 podcasts, one with my good friend and colleague Bryce Lelbach called ADSP, and another called Arraycast, which is super relevant to this talk. If you like the material that's covered in this talk, you'll probably love the Arraycast podcast. So if you're interested in any of this stuff, like I mentioned before, links will be down in the description below. So in this presentation, I'm going to be comparing several different solutions from different programming languages of a single LeetCode problem. And that problem is entitled Check If Matrix is X Matrix. I'm not going to read this problem statement. If you want, feel free to pause the video and resume after you finish reading it. I think it's easiest to understand this problem, though, if we just look at a couple of examples. So these are the 2 examples that LeetCode gives us. And basically, you're going to be given a matrix, specifically a square matrix that has the same number of rows as it does columns. And you're asked to return true or false, true if the square matrix is an X matrix. And an X matrix is a matrix that has zeros everywhere other than the diagonals. So on the diagonals, it expects to have non-zero values. And if you look at the matrix on the left, you can clearly see this is the case, but for the matrix on the right, it is not the case. We have non-zero values not on the diagonals, and that is not what we're looking for. So in summary, matrix on the left, you return true, matrix on the right, you return false. And from here, we're just going to look at the solution sort of step by step of how we're going to solve this. And then we're going to look at the different solutions across the 3 APL, BQN, and J. And then after that, look at R, NumPy, Julia, and Q. So first, we are going to store our first example of the 4x4 square matrix into a variable called mat. And the way we do this is just with a for reshape of our data. And that's going to give us our matrix like this. So we're going to wipe off the sort of for reshape, and we just are going to know that in mat is stored this matrix. So the first thing we're going to do is build up an identity matrix, which is a matrix with 1s across the main diagonal. And in order to do this, we first need to know how many rows or columns, and we can do that with tally. Tally basically gets you the number of main frames in your matrix. So for matrices, that's going to be rows. Another way to state that is it's just going to give you the first element in your shape, or the main dimension, or the first dimension in the shape of your matrix. So in this case, because it's a square matrix, it doesn't actually matter. You can either get the number of rows or columns, and we get 4. From here, we want to get an iota sequence from 1 to 4, and so we just use iota for that. And from this, we now need to use this iota tally mat as 2 different arguments to a binary function called outer product. So binary functions are infixed. So you can see here we basically have our 2 arguments, iota tally mat, both on the left and the right. And then our binary function here is in the middle. The jot dot is an outer product, and then this is a binary function that we combine in order to make our full outer product. And this binary operation is catenate, so it basically just makes a pair of numbers for each of our sequences. So we're going to end up with 1 paired with 1, 2, 3, 4 on the first row, 2 paired with 1, 2, 3, 4 on the second, and so on and so forth. And the nice thing about outer product is that you can replace this binary operation catenate with any binary operation you want. And if we replace that with equals, you'll end up with your identity matrix. So note that the only place in our matrix before where our pairs of numbers are equal to each other is along this diagonal. So it works really nice like that. So this is how you one way to get an identity matrix. But what's really irritating about this is that we have our argument, which is the same both on the left and the right, duplicated, which is kind of redundant. So we can use something called the W combinator. This is known as self or selfie in APL in order to basically avoid that redundancy, which is super, super nice. And this is going to come up later. Now, in order to turn this into an X matrix, you basically just want to combine this left to right identity matrix with a right to left identity matrix, which is basically just the reversal of the matrix that we just had. So if we take the matrix we just had and find a way to combine this with the reversal of that, then we're going to end up with our X matrix. So there's a couple different ways to do this. On Twitter, someone pointed out that you can do this with logical OR. I'm going to do this with maximum. So if we insert a maximum glyph in between these two matrices, we end up with the X matrix that we desire. And this, once again, is a little bit irritating because now we have two different sequences, the jot equals self iota tally mat, that are identical other than the reverse at the front of the left one. That's completely repeated. So once again, we can make use of a different combinator. This one is a fork, which we're going to need to find two unary functions in front of our similar sequences of operations with a binary function in the middle. So our binary function is a maximum. Our unary function on the left is reverse, but we don't have a unary function on the right, and that's because there is none. Well, there is a unary function that we can use called identity, basically, or same, and this just basically gives you back what you passed into it. So now we have our unary function with a binary function in the middle, and we can move all of this stuff to the left, and then, once again, avoid the redundancy, which is super nice. So this is what's called a fork in APL, and we'll come back to this in a bit. So now we have our X matrix, and what we basically need to check is our original X matrix somehow equal to this? So if we go back to our original matrix, we just basically need to check, is this, equivalent somehow to an X matrix? And the way we can check that is if we just do a 1 minimum with our matrix. So for every value, take the minimum of the value in 1, you'll end up with an X matrix if this is actually an X matrix. And now that we have this, we basically just need to check, is this equal to the X matrix that we generated from that sequence that we just had? So if we bring back that reverse max same jot equal tally or jot equal self iota tally, we now basically just need to check, are these two equal? There's an operation for that in APL called match. And if we do that, we're going to get back a 1 or a 0 for true or false based on whether your matrix is an X matrix. So from here, we can replace the mat with basically omegas and then put it inside of braces, and that's our function. And then we can assign this to check matrix. So omega is just the glyph that you use for an argument in a single argument function. And that's basically the solution. So we can compare this to BQN, our next array language, and it looks somewhat similar. And then if we compare this to J, it's going to once again look somewhat similar, although we no longer have Unicode characters, we have digraphs and single ASCII characters. And if we juxtapose all of these next to each other, we end up with the following. So very similar, although they kind of read differently. But if you are familiar with all of these languages, you'll be able to see the similarities. But we can make this easier to compare across these three. First thing we need to do is get rid of the function names because they're redundant. So if we get rid of the function names, everything's a bit bigger. And then we're using the same color syntax highlighting here, but every language decides to assign the different colors from the theme to different operations, functions, operators, etc. So I manually went through and unified them so that they're all the same. And then once we've done this, we can just align things so that the parts of the operation align better, so it'll make them easier to compare. And from this point on, we are now going to look at sort of the 4 different main characteristics that I want to cover in this talk when looking at array languages that I think are extremely important for why I love array languages so much. And those 4 things are the following: rank polymorphism, operators, combinators, and leading axis theory. So we're going to go through these one by one and look at how these show up in the solution that we just covered. So the first one is rank polymorphism. So instead of explaining what this is, I'm just going to show you via example by once again looking at our solutions. So the places where rank polymorphism comes up are basically these 2 verticals. So we have the one on the left, we are taking basically a scalar, aka just a single number, that's known as a rank 0. That's what R0 stands for. So a scalar, a single integer, and then performing a binary operation element-wise with a rank 2 matrix. And this is super nice, so this works. And the one on the right, if you recall, if we focus on the APL solution here, we've got basically 2 different matrices, the original one and then the reversed one. And then we're using, this is minimum, this is max, but you can, for the purposes of this explanation, you can consider them just to be the same. And we have this max operation happening basically on 2 matrices. So we have a scalar with a matrix and a matrix with a matrix. And this is something that for a long time I didn't really think was that important. But the more and more I've started to go back to languages like Haskell or C++ that don't have this built in, it becomes extremely cumbersome when you are used to having it at your disposal all the time. And that's because these binary operations are implemented from the language point of view for all different ranks, arbitrarily ranked arrays. So it doesn't matter if you have a scalar and a matrix or a matrix and a matrix, this always just works. And to highlight this, it's useful to compare what this code on the left, the 1 min with our matrix, what that looks like in a language like Haskell, which is another one of my favorite languages and is also, compared to C++, quite terse and expressive. So this is what taking the minimum for every element in a matrix looks like in BQN with a scalar, and this is the equivalent in Haskell. So when you don't have rank polymorphism built into your functions and your operators, you have to explicitly map any time you are dealing with different ranked sort of arrays. In Haskell, we don't really have ranked arrays, we have lists, but you can imagine if X is a list of lists, in order to take the minimum of each of the elements in each of the lists in your outer list, you have to map a map of min1. And I'm not saying that every language needs to have this, definitely not. I'm just saying that this ability to use your scalar operations and all of your sort of functions that come with the language, they are implemented on the language side so that you don't need to worry about this when you're using your scalar operations and your functions, which I used to think this wasn't a big deal. And then I think it was one time I was dealing with a rank 2 or a rank 3 array, and I went to go do the equivalent thing in Haskell or C++, and then I ended up writing like 2 or 3 different maps or 2 or 3 different stood transforms. And it's one of the reasons that if you're dealing with a problem that makes use of higher ranked arrays or matrices, array languages are super, super powerful. So that covers rank polymorphism. Moving on to the second thing that I think is amazing about array languages is operators. The confusing thing about operators is that these are named differently in almost every array language. So Dialog APL refers to these as operators. J and Sharp APL and Dictionary APL refer to these as adverbs and conjunctions. BQN refers to these as modifiers. So depending on not just the language, but the dialect of the language that you're using, we refer to these as different things. In general, I think about these as higher order functions. Functions that take functions as their arguments and then return functions. And we can see this in a couple different ways, but the main one that we're going to look at is basically the outer product. And this is known as outer product in APL, and it's known as table in BQN and J. And if you're not familiar with outer product, you sort of saw it earlier, but once again, you basically have 2 sequences, and then you give your outer product higher order function, a binary operation, an operation that takes 2 arguments. And from that, it's going to basically create a table, which is why they named it table in BQN and J. And if we take the plus binary operation, for example, it's just going to combine all pairs of numbers in table form and apply that binary operation to each of your pairs of numbers, which is super, super useful and doesn't show up in many languages other than array languages. On top of outer product, there are many, many operators or higher order functions in array languages. The three main ones, in my opinion, are reduce, scan, and outer product. This is a table taken from my array language comparisons GitHub repository. You can see the first three are APL, J, and BQN, and all of them have rich support for these three operators. Q as well has them, and almost all other array languages have them as well. You can see that there are yellow dots for languages that have some kind of partial support or a corner case that doesn't work. I'm not going to get into that here, but you can tell that Julia uses broadcasting that for most purposes, you can replicate exactly what happens for outer product in array languages. The point is that most array languages have rich support for these operators or higher order functions. I'm just showing the main three here, but there are a ton of other operators or adverbs and conjunctions or modifiers in BQN, J, and APL that basically take the higher order functions that exist in functional languages like Haskell, but make them, bread and butter tools that you're always reaching for, and the power and expressivity that you get from it is amazing. Going on to the third thing that we're going to cover from our list of 4 items is combinators. Now, I could spend a whole hour or 2 hours talking about combinators and combinatory logic. I've alluded to this in several other talks that I've given, and rest assured, if you are waiting for my combinatory logic video, I will be giving a 1 or 2 hour talk at some point in the next year that is going to be focusing on combinators and combinatory logic because it's something I'm super passionate about and not a lot of folks know about. For these 3 languages, though, we're going to look at 2 different examples. The first one is the W combinator. So this is what was referred to as self or selfie in APL. In BQN, I believe it's also called self, and in J, it's called reflex. You're basically given a binary operation, and when you use it with this combinator, it turns that binary operation into a unary operation and duplicates the argument that you pass to that unary function to basically both argument slots in the binary function. So we're using equal, 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 and then we've got table, table, and outer product in order to do that. So anytime you end up sort of duplicating an argument, you can avoid that by using the W combinator. In Haskell, they call this join, and in other languages, it comes in other names. The second and more interesting combinator example is in this vertical, though. So you can see that the fork on the first line in APL is known as the phi combinator in combinatory logic. At the bottom, we have the S combinator. That's probably one of the more popular combinators because it shows up in the SKI combinatory logic and the SK combinatory logic. And then sigma isn't really officially a combinator, but it shows up in my master's thesis as kind of the reverse of S, which I'm not going to talk about here. I'll save that for my combinatory logic video. On top of this, there's actually 2 more spellings with 2 different combinators. So in BQN, the reverse of sigma is the S, so it's similar to the J solution. And then although APL doesn't have the S combinator, you can combine the D and the W combinator in order to basically get the behavior of S. So you might notice in sort of my explaining these is that if you combine D and W combinators, you get the S combinator, which implies this kind of hierarchy. And even on the second line here in our fork or phi combinator, we're making use of the identity function, which corresponds to the I combinator. And so really, when you're using a fork and you have either the I combinator on the right or the left for one of your unary functions, this corresponds to the S or the sigma combinator. Once again, I probably lost all of the listeners. Stay tuned for my combinatory logic talk, which will probably be called Composition Intuition. And I'm going to delve all into that. But the point is that there's a lot going on here, and it's super, super important in my opinion. This is a graphic from my master's thesis that basically points out is that these combinators can be hierarchically represented in a diagram as following. So at the top is D2, and as I mentioned, if you have the phi combinator and you specialize one of the unary functions to be the identity, the I combinator, you'll end up with sigma and S, and D plus the W combinator will get you S. Anyways, I'm gonna say only one more thing, and that's if we compare this to the combinators that exist in BQN, you can see basically that all of these combinators in the combinator hierarchy can be found in the BQN language, which is actually why BQN is my favorite array language of all, is because it has the richest support for combinators. That's all I'll say for now. Stay tuned to my composition intuition talk. Moving on to the fourth item of 4 that we're looking at when comparing these 3 solutions, and that is going to be the leading axis theory. So this is actually something that I only learned about sort of recently in the last 6 months and sort of understood fully. I made it a full basically 2 years without fully grasping what leading axis theory was or meant. And this shows up when we take a look at our reverse glyph. So they're identical in APL and BQN. J, because they don't use Unicode, has a pipe dot to represent the reverse, but they mean the exact same thing. And as you might guess, if you take a rank 1 array and you reverse that array, it's just going to reverse the order of the elements. So if you have 1, 2, 3, you're going to end up with 3, 2, 1. What's interesting is when we increase the rank of our array from 1 to 2. So right now we just basically have a vector, but if we increase the rank to 2 so that we have a matrix, now what would you expect? I would expect that all of these do row reversals. But the actual fact is that the only one that does a row reversal is APL. And BQN and J both do column reversals. And that's because the reverses in BQN and J are both leading axis functions or symbols. And what that means is they follow sort of something called leading axis theory, where you always operate on the leading axis by default. And the operator or function that we're using in APL is actually a trailing axis or last axis function. And there is a leading axis APL function, and that's the one up in the top right-hand corner. So this looks like it's a better symbol because it actually corresponds to the one where you're reversing columns, whereas visually, it looks like the one with the sort of vertical line through it is reversing rows. So to break this down in table format, there's sort of one way to reverse columns in APL, BQN, and J, but then there's multiple ways depending on the language except for J. So you basically want to modify the rank that your reversal is working on when you're using a leading axis operator. So if you want to reverse the rows in APL, you can use the sort of trailing axis function reverse, or you can use what's called the first axis reverse, or reverse first. And once you do that, you need to basically modify it to use rank 1. So you can see the 3 different symbols for rank. One looks like a sort of emoji, the circle with the sort of half circle inside of it, and then the double quote are all the rank operators in APL, BQN, and J respectively. And very nicely in BQN, for a lot of very common sort of rank modifications, they have shortcuts. So this is something called cells, and it's basically just a different spelling of rank 1 because it's so common. And the jury's out on which I think is actually best. I mean, I think that the leading axis model is definitely the best model, but it's not necessarily the easiest to learn. So I think there's a trade-off between a language like J that doesn't have a way to reverse rows without learning the rank, whereas APL, I made it 2 years in APL without understanding rank and realizing that there was a different way to use a sort of first axis function and modifying it with rank in order to get the same behavior here. So maybe if folks have questions at the end, or they can ask them in the chat now, and I'll be happy to answer them. But that's all I'll say, is that leading axis theory is a thing that affects these languages differently. And BQN and J by default kind of have leading axis operations, and APL has both leading axis and trailing axis. So many people will argue that with leading axis, you don't need multiple glyphs, but then it's potentially a more difficult language to learn. So there are trade-offs between the 2 models. That being said, we've gotten to the end of our 4 different criterion: rank polymorphism, operators, combinators, and leading axis theory. So now we are going to look at our Q solution, then our Numpy solution, I think then our Julia solution, then our R solution, and one last thing. So up next is our Q solution. We don't have a logo for the Q programming language, so we're going to use the logo of the company KX that was acquired by First Derivatives that owns the language. And the first thing you'll note that this is a little bit more verbose. We've got some semicolons, and I'm not even sure if you're allowed to reformat the solution this way, but that's the way we're going to do it. And the big difference right off the bat is that we have a bunch of temporaries. We solved the previous 3 solutions in APL, BQN, and J all in a single line. But because of the lack of support for combinators, we need to basically store things in temporaries so we can reuse them in multiple places. Note that we need sort of the matrix, the identity matrix, twice, I, and we also need n, or we need the array, the sequence from 1 to 4, twice when we do our outer product. Otherwise, it's basically the same thing. Till is iota in Q, count is tally in Q, and this is a sort of ugly way of spelling outer product. Technically, you don't need to do the full verbose way. You can, I think, do an each left or each right, but that'll give us our identity matrix, and then we're doing our max of our original identity matrix and the reverse of it. And then we're doing something slightly different here due to the fact that we can't compare Boolean matrices with numeric matrices. So we basically need to get the matrix. We can't just do a min 1 because that'll end up with the numeric matrix. But if we do a not equal to 0, that's one of the methods that you can get a Boolean version of our numeric matrix. And then if we just check if this matches, we're good to go. So this is basically the case solution. And note that the biggest difference here, I think, is the fact that we don't have support for combinators, the W combinator, and either the S combinator or the phi combinator. Therefore, we need to store things in a bunch of temporaries, which in many of your opinions might make this more readable, but it's just something to highlight. And we can see this explicitly if you've been following along on my YouTube channel or on Twitter. I released a behind the scenes of the Arraycast episode 36 and also tweeted this out in the last week. This sort of diagram that shows the delineation between array languages, Iversonian array languages, aka languages that derive directly from APL or its descendants, functional languages, and then combinator languages. And you'll note that KX falls in the Iversonian circle of languages, but outside the combinator languages circle. So J, Dialog, APL, and BQN are the only Iversonian languages that have good support for combinators. With that said, let's move on to the NumPy solution. So from here on out, we're going to look at 2 different solutions for each because all of NumPy, Julia, and R have support for a built-in function that gives you an identity matrix. So it'd be unfair to sort of show one and not the other, but this is probably what you would write. You've got numpy np.identity, so you don't need to worry about the W combinator or using outer product because you just have this built in. And then once you have your identity matrix, you've got a lot more verbosity, but basically still the same thing happening. So your np.minimum is basically doing the rank polymorphic minimization of your initial grid with 1. And then on the second line of our array equal, you have np.maximum. And this is with our identity matrix, and then the reversal row-wise of our identity matrix I. And so once you have these two, you have to do array equal that'll compare the whole array, and you're good to go. So once again, no support for combinators. So you see the duplication of I and I. It's hidden, the duplication of the fact that you need sort of the iota sequence twice, but that's because we have our identity function. But if we look at the more comparable, if we actually have if we don't make use of the identity function and we just use outer product, what do we get? Basically the same thing, other than the fact that we're not using np.identity. So NumPy is interesting in that it sort of hard codes all of their quote-unquote higher order functions. So instead of calling outer and passing a binary operation to it, you call outer, which is implemented on all of the built-in binary operations. In this case, what we want is equal. And this works. It's not super generic the way I would like. And at one point I posted on Twitter saying that, you know, NumPy doesn't have support for a true generic outer product. But then someone pointed that in NumPy and Python, you have something called a from pyfunc that you can actually call with a generic outer. So to some extent, you do have outer product. It's just not as nice or generic as I would like. And once again, we now see the duplication. So I could have stored this iota sequence, which you get by calling a range with n in a temporary called x or a, as we did previously. But it seemed, this is why I like combinators so much. You don't need to choose when do you store something in a temporary or when do you not, because it's really just for, you know, I don't know. It's I mean, in any, I guess it's an interpreted language, so you're doing twice as much work here. So maybe it is actually useful in Python to store this into temporary, so you're avoiding that extra work. But in a sophisticated enough compiler, it should be able to see through that these are the same things and not generate it twice. Anyways, though, enough about the NumPy solution. Still pretty nice that we can get a very sort of APL-inspired solution. Moving on to our second last solution, which is Julia. Once again, we're going to look at two solutions. Here, the identity function is called I, which you need to pipe to matrix as well. So our tally or length function is called size. Note that Julia is sort of axis agnostic. So if you ask for the size of any arbitrarily ranked array, it'll give you the count of all the elements regardless of the rank. So in a 4x4 matrix, size without specifying an axis or a dimension will give you 16. So you need to specify, so this is honestly kind of like a rank polymorphic size. And so they don't have the equivalent of an APL tally. But once you do this, pipe that to I, which gives you your sort of identity values, and then you need to pipe that to matrix to get it in matrix form. And then you end up with your identity matrix. And here it gets very interesting. So you use your equal equals to replicate the match in APL and the NumPy array equal. But you'll note here that we're using min and max, but they have this period notation. So there's a couple different ways to spell this. You could spell it out full farm using a function called broadcast. But on prefix functions, you can postfix a period and turn that function into a broadcasting function. And on binary operations that are infix, you prefix it with a dot, which is a bit confusing. But the point is on different types of functions, you either put a dot before or after, and that turns that function from a binary operation to a sort of broadcasted binary operation. And what that means is it'll do an element by element comparison, and behind the scenes, it'll match up the rank. So here we end up with two matrices. So we just end up doing element by element and pairing them all up because the shapes already match. But in this case, where we have a rank 0 scalar and a rank 2 matrix, it will broadcast this scalar to do element by element wise for each of the elements in grid with the 1. And note here, once again, in order to sort of do our rank polymorphic modification of reverse, we just specify the dimensions that you want it to operate on to be 1. So broadcasting, not sure if I love it. I'm still learning these languages, but interesting to see sort of the differences between these. And once again, the second solution in Julia, if we don't make use of I, the identity function, we are going to end up doing a broadcasted. So once again, I just mentioned on prefix functions, you put the period after the function. On binary infix functions, you put the period before. And here we just are basically doing an iota sequence from 1 to n, 1:n. And you broadcast this with the equal equals binary operation. But note that you have to do a transpose here. And this is the reason for the yellow circle in Julia. Whenever you have two equally lengthed rank 1 arrays, you're basically just going to end up with a zip width or a two-range transform. So if this was 1, 2, 3, 4 on each side, you just basically get back a rank 1 array that was true, 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 because you're checking whether each element. But you don't want that. You want the rank 2 matrix that creates the table. And in Julia, I think the idiomatic way to do this is to transpose one of your rank 1 vectors or arrays, which changes it into basically a rank 2 matrix with 1 column, which I think is incredibly broken. Transpose should never change the rank of your array, but it's what Julia is, how Julia was designed. So transpose on a rank 1 array increases the rank from 1 to 2. Say what you will, this is the Julia solution not using I, the identity function. And last but not least is R, which is, I guess, probably the oldest, especially if you include the lineage of it going back to the S programming language. Once again, there is an identity function in R called diag, and it looks pretty similar to the two previous solutions we've seen, just different names for things. So instead of identity or I, we have diag here, n row for the number of rows in grid, and then I is your identity matrix. And here we don't really have an axis or a dimension to specify as we did in the NumPy and Julia solutions. We have to make use of this apply. There's several different ways to do this in R. I'd definitely say R is my least favorite of the 3 last languages that we've looked at, but say what you will. You can call equal to check that these two things are going to be equal, but note that you have to call all at the end. So this is actually an element-wise operation that's going to return you a rank 1 array of Booleans, and then when you call all, it'll check to see if all of the elements were equal. So there's no broadcasting, and there seems to be a mix and match of how these operations work. So note that we're calling pmax and pmin. This is when you want basically the rank polymorphic behavior and element-wise operations to happen. If you were just to call max and min, it wouldn't work here because max and min are defined as binary operations similar to how they are in Julia, but that work on 2 arguments that are scalars. And if you pass them anything else, it's not going to work. So whereas in Julia, you had basically the broadcasting functionality where you prefixed or postfix your functions with a period in order to make them element-wise operations. In R, you have entirely different functions that are just named differently. So pmin and pmax. I definitely don't love this. I like the broadcasting in Julia better. I like the rank polymorphism that exists in APL, BQN, and J even better than any of these options. But once again, it's just good to highlight the differences. And yeah, that's just my personal preference. It doesn't necessarily mean one is superior than the other. And last but not least, the alternative solution in R, which doesn't make use of the built-in diag identity function. And this one's actually quite nice in that there is a built-in outer product function in R, and it takes your binary operation as the last argument as a string. Why it has to be a string, not really sure. Don't know enough about R, but at least it has outer product built in, and you're not doing any weird things where you have to transpose a rank 1 vector to get a rank 2 matrix of 1 column. This middle line of code I prefer much more. But once again, no combinators in any of the NumPy, Julia, or R. So you're seeing this replicated sort of N everywhere and I everywhere, which isn't the end of the world, but it requires us basically to store these in temporary so that we only are repeating a single letter, whereas if we were to repeat this whole line, that'd be quite irritating. But you can get around this by using combinators like the phi, s, and w combinators in the first 3 languages that we looked at. So here we have gone through all 7 of our languages now. Let's take a look at the last 4 very quickly, how they line up against the 4 criteria that we looked at: rank polymorphism, operators, combinators, and leading axis theory. Now, I'm actually not 100% certain about all of this stuff. This is just my rough take on having learned about these languages over the last month and a half or so. And even the green checkmark that I've given Julia for operators, I still feel bad about due to the fact that it doesn't have a fully working outer product. It uses broadcasting that has corner cases that don't really work. But for most things that I've looked at, Julia has the best support for higher order functions that just accept binary operations to modify their behavior, like reductions and scans. And so the point is that you could have colored these all yellow, but I wanted one to be green, and I thought the closest to any of these things being green was Julia with their support of sort of higher order functions. So note, none of the languages have support for combinators. Very sad. I love combinators. None of the languages choose leading axis theory as their model. KX, I think, is the closest, but they don't have a rank operator. So it's kind of hard to have a leading axis theory language if you don't have a rank operator, because you end up doing weird things with each left and each right. But it still gets a yellow check mark because if you do reversals on a matrix, a rank 2 array, you will get back sort of reversed columns, and then you just need to do a reverse each to get the rows. In terms of operators, all of these languages to a certain extent have support for higher order functions. Maybe Q, aka the KX logo, should have a green check mark. But once again, doing outer product is actually a combination of each left and each right, and depending on the binary operation, sometimes you don't need the each left and you can do it with just an each right. Just the model seems not as regular and complete when compared to APL, BQN, and J. So people might argue in the comments of whether this is fair, but it's just my initial feelings based on sort of learning about the language over the last bit. And rank polymorphism, I mean, technically you might say some of these deserve green check marks, but you know, NumPy, like I said, they've got kind of support for it. KX, once again, kind of has support for it, but no rank operator. It's just potentially I'll revisit this and give some of these languages green check marks. The yellow indicates at this point in time that they are different than the rank polymorphism that exists in APL, BQN, and J, which I think sort of works the most comprehensively. But just because it's different doesn't mean it's worse. Anyways, just wanted to pause sort of on the 4 things we looked at. Last but not least, the final thing I want to say in this video is that there's a 5th thing that I haven't really talked about, which arguably should have been the first thing that I talked about in this presentation, which was the fact that array languages operate on arrays, which obviously is obvious, but what it means is that you end up with code that doesn't look anything like this. So I'm a professional C++ developer. There's many ways you could solve this problem, but a lot of C developers and C++ developers are going to do something like this: a doubly nested for loop with 2 indexes, I and j, or choose your single letter index that you want. And then you're doing some checks element by element and making sure that, on the diagonals you have a non-zero value and everywhere else you have a 0 value. Otherwise, you're going to short circuit and return false, but if you get to the end, you return true. I find this very irritating. First of all, this isn't even correct. There's a less than equal to on each of the for loops. It should be less than because it's 0 index and it has to be less than our size, a common off by 1 error that folks make all the time. And it's still broken. There's another off by 1 error. You need to do a +1 to your j in order to make sure that you're checking the right diagonals. So there's 2 different mistakes in this code, minus the mistakes that are very common because you're dealing with indices, and off by 1 errors are one of the most common errors that programmers make. You're not operating on arrays. And with our BQN, J, and APL solutions, we end up with code that is operating on whole containers. And you don't need to worry about indices. You're reversing rows. You're creating a matrix from a scalar, which goes from a scalar, a rank 0 array, to a vector, a rank 1 array, up to a rank 2 matrix. But you never have to worry about indexes or off by 1 errors. You're using combinators to reduce redundancy in the arguments that you pass along, and it's just nicer to operate on whole arrays, whether it's rank 0, rank 2, and you don't need to worry about writing, 10 different lines of C++ code with indexes I and j, where the opportunity to shoot yourself in the foot is way higher than when you're using these operations that take arrays as arguments and return you arrays. Thanks for watching. I hope you enjoyed. I probably have been answering questions for the last 40 or 45 minutes, however long this talk ended up being, but I will hang out in the chat even after this video ends. I think the chat will continue to go on as long as you don't close out of the video. And if, like I said at the beginning of the video, if you have questions and you're watching this after the live chat, feel free to put them in the comment section down below. And yeah, thanks for watching. I hope you enjoyed, and I will see you in the next video.